It's a pleasure to be here. I was here just on Wednesday talking to the, what year was it? It was several years or something. Oh, have I pressed? I thought you were going to do that. So I have people that do that.
This isn't the BBC now, you know.
It's ridiculous. Just can't get the staff. So, yeah, let me start that again. So, it's a pleasure here. I was here on Wednesday talking to the kids in terms of some of the things I'm going to talk about. It's a different talk. So, yeah, Scotland Rocks. I remember that title appeared in a little advert in some geology journals because BBC Scotland were looking for a presenter for a programme on Scottish geology, probably in the late 90s. And I remember applying for it, and then nothing happened. It just went away, and I kind of forgot all about it. And then I started in television, and then I suggested this programme, and the BBC went for it, and they ended up kind of something called Men of Rock. And the thesis of Men of Rock was, how come this tiny little bit of real estate that is Scotland has spawned many of the great ideas about the planet? And it's, of course, it comes out of the Scottish Enlightenment and really the kind of centre of gravity of intellectual thought that was particularly Edinburgh, but west of, in central Scotland. And amongst geologists, Men of Rock tends to be a favourite. A lot of geologists tell me, and the reason is because it talks about the people, the characters that's involved. So I'm going to mention some of this. So yeah, it's going to be this notion that much of what we know about the planet, we know because Scots-based or Scots-born people have worked on this. Geologists are odd people because that is the world, and you all know it's the world. You've all recognized that from the first time that you open up an atlas when you're 5 or 6 or 7 years old. And you can almost close your eyes now and see those continents. It's kind of spaced out. And if I gave you a bit of paper, you could make a hash of what it was. It might be a bit funny, but you would recognize the Americas, Africa, Eurasia, Australia, and Antarctica. And so that is an iconic image. But if you're a geologist, that's not necessarily the way you look at the world, because that is a snapshot. That is one moment in time in a period that's been 4.5 billion years. So the planet's been constantly changing. And if you were an alien spacecraft that appeared 200 million years ago, you would see a very different planet. And that's the thing about being a geologist, is that part of the trick, part of the challenge of being a geologist is keeping in your mind both the worlds out there today, that's the easy stuff, but keep in mind these multiple worlds that are constantly changing. So if we were an alien spacecraft coming up 200 million years ago, what would we have seen? Well, we would have seen the world like that, actually. That's what it would have been. And that looks decidedly odd. For a start, there we are, right in the middle. There's the UK, Britain, sitting juxtaposed beside Greenland and Norway, no Atlantic, no Iceland, actually. You can see how beautifully South America fits into the side of Africa there, two of them stuck together. You can see things like, for example, the southern Mediterranean countries, Greece and Italy, Turkey, actually part of North Africa. And most impressively, you can see the southern continents all beautifully tucked in. There's India beside Madagascar, beside Antarctica. There's Australia, cheek by jowl with Antarctica. That's a very different world to the one that we're familiar with. And yet every geologist on the planet knows that world. It is a fundamental element of our understanding, because really it's from the breakup of that world that we now get all the scattered, distributed continents of today. What's interesting is, ever since there was the first maps, people kind of highlighted, particularly the nice fit of Brazil and Africa. But one of the first people, almost every Tom, Dick, and Harry that made a world map actually ended up kind of noting that Africa and Brazil seem to be connected. But one Tom Dick actually, the Reverend Tom Dick, actually made the point of saying, and they wrote in such excruciating text, this is 1844, that he talks about a consideration of these circumstances, and these circumstances is that the two continents fitting together, renders it not altogether impossible that the continents were originally composited, and that at some favourable physical revolution or catastrophe, they may have been rent asunder. I want to get rent asunder into a science paper. I just think it's brilliant. Now, the paradigm of the day, of course, was the Bible, and for the Reverend Dick, he was thinking that this was the flood. That this rent asundering was the flood water spilling out and producing the Great Deluge. But that was really that was a very cogent argument that there was some physical process that was responsible for this. It would be another half century before earth scientists put the evidence together to actually be convincing that there might have been something. And even then, it was completely rejected by the physicists who said it was physically impossible for this to happen. And what was interesting was the Reverend Thomas Dick was extremely, he was a Scottish clergyman who wrote lots of different books about, he was up in kind of on Broughty Ferry, he had set up an observatory there, he published lots about astronomy, but he also, in a way, that great polymath of the age, he wrote about the human condition. And he was the person, one of his books was the book that actually inspired David Livingstone, for example, to go to Africa in the way that he thought about the world. And I just want to kind of take that Livingstone theme up a little bit and show this introduction. Because what I want to do is, that clearly isn't the world we have today. So how did we get to the world that we've got today?
The discovery of Africa's deepest origins started with Livingstone's fateful expedition 150 years ago. As he made his way down the Zambezi River, Livingstone found his progress suddenly interrupted by a strange sight. A huge curtain of mist rising up from the river ahead, accompanied by a steadily increasing roar. Leaving his team behind for fear of putting them in danger, the explorer continued his journey on foot, only to find his way blocked by the most impenetrable of all obstacles. Known to the locals as Mosi-oa-Tunya, the smoke that thunders.
We, of course, know it as the Victoria Falls.
And the ultimate way to experience the falls involves getting your feet wet.
This is the way to see the Victoria Falls. Oh my gosh.
While the water around me cascades down more than 100 metres to the river below, this pool forms a hidden sanctuary.
Do that. You've got to promise me, when you came in and signed up, you've actually signed up to do that. Only make sure you go there in September, otherwise you'll be in a very different situation where you'll be actually swept over there. But that is the most extraordinary place. There's this Livingstone's kind of memorial, and it is that iconic landmark. You know, as I say, people ask me how I get into geology, and I never had a little fossil collection. I never had a mineral collection. I don't think I kind of hill walked and climbed and things like that. What I did have is I liked adventure books, and I thought you actually could be an explorer. I thought that was a job or something like that. And it was people at Livingston that was fundamental to that. So to go there, and not just to see the falls, I mean, that's pretty extraordinary, but to understand what that whole landscape is telling us is really crucial. And so this next clip is a kind of sciencey bit. This is a sciencey bit that explains what actually is going on and why that place is so important.
You can see exactly what happened here 180 million years ago by looking in the vast gorge beneath the falls. Because hidden in the rocks is some intriguing evidence of a cataclysmic geological event that would create Africa as we know it today.
What a place! It's like an amphitheatre of rock. The thing is, all these cliffs are carved from the same rock, a rock called basalt. And it comes to us from deep underground, rising up as molten magma. To appreciate basalt, to understand what it's trying to tell us, you have to get inside it though.
In here are the secrets of its formation.
Crystals cooled really rapidly. You see it's a slight speckled appearance, which if you look with a hand lens, you can see is lots of tiny, tiny crystals.
These crystals were formed as the hot rock cooled, and their size tells you how quickly it happened.
So what this is telling us really is that this rock must have cooled really rapidly.
Sudden cooling of searing hot magma means crystals don't have time to grow, which is why they're so small.
And one way to rapidly cool a rock like basalt is to erupt it from the surface, expose it to the air, and it just solidifies very quickly before the crystals can grow. So all of these rocks here, all these basalts, were erupted out as lava flows.
Lava flows that reveal their size in the soaring cliffs.
What takes your breath away here is just the sheer scale of the eruptions. I mean, that cliff there is 120 metres high, and it's just layer upon layer upon layer of lava flows. And the thing is, that continues down underneath for hundreds of metres. I mean, across this region, it's thought that over 1 kilometre of lava was erupted out in 1 million years or so. It must have been the most staggering volcanic event.
These eruptions were the start of an immensely destructive event that happens only rarely in the Earth's history. It would have stretched for thousands of kilometres, burying huge swathes of what was to become Africa under millions of cubic kilometres of molten lava. The cause of this mayhem was one of the Earth's most powerful forces. Huge upwellings of superheated rock called a mantle plume. The sheer force of those mantle plumes making their way towards the surface pushed the land up, causing it to thin and crack. Cracks which eventually got so big that the land slowly began to fragment. So beginning the breakup of the single largest landmass the Earth had ever seen, Pangaea. As the supercontinent began to split apart, one by one the Earth's continents were torn from its outer edges. The eruptions at Victoria Falls led to the formation of India and Antarctica. Another mantle plume cleaved off North America, then South America, leaving behind Africa as we know it today.
So what that story is starting to say, is talking about, is that great fragmentation of that continent had a series of splits. One of those splits was in Africa, and the great outpourings there, it's created that fantastic landmark that is the Victoria Falls. It's interesting. You don't have to go far from this place to find the equivalent features. You can go to the Campsies and you find plateau lavas built up layer upon layer upon layer from a much, much earlier episode. You can go to the west coast of Scotland and you can find plateau lavas that are the Giant's Causeway, Fingal's Cave, these areas where the Atlantic starts to split up. So the kind of processes that we see in certain areas, we see them all over. That is the way that geology actually works, is that we take from what we can see around us and then we export that back into the past by reading the rocks. So this image then here is really an artist's impression of the birth of the Atlantic. It happens 201.5 million years where the first splits occur, round about where New York is. At the moment, New York, that east coast would have been sitting cheek by jowl with North Africa. And we capture this as 166 million years. So actually over in Africa, we've already been, those splits have happened that formed the Victoria Falls. What is extraordinary though, is that we now have the most amazingly detailed views of some of this. These images are from satellite-based measurements of gravity. And I'm not really going to explain them too much, but I'll just go through them and you can see the intricacy by which we can now image the breakup of this great continent. This continent was called Pangaea. We've actually started this at that point of 160 million years, so it's had 40 million years of split. We're already, so there's a kind of narrow seaway has started to develop, which is what is this going to be the central Atlantic. You'll notice that the southern Atlantic really hasn't started to open. And you'll see that up here, there's been really we're not starting to open anything really there. There are some splits, we'll see this in a minute. And I'm just going to move through some of these. I'm not going to go through, but I just think these are beautiful. And so this is the latest kind of technology and how we look at the planet. Jump forward 20 million years. What do we see? The Atlantic steadily opening. And we see the splits happening down here. So we're starting to get activity. The thing that I love about geology is that it kind of solved lots of these geopolitical issues. If only the world would listen to geologists, it'd be a much better place. So we have a fight about who owns the Falkland Islands, is it us or Argentina? And actually, one of the interesting things is that geologically, the Falkland Islands are part of South Africa. Why don't we just sort that out? That's a new political one now. South Africa is at this moment writing in, requesting the... but what we're going to see is, we're going to see this will break up, we'll see this break up. So we jump forward 120 million years, Atlantic now starting to get quite sizable. We can start to see development now in the south. The north is still unattached, and we just take it forward to 80, and then to 60 million years. And you can see, for example, let's now switch, the Falkland Islands are just there, they were over there. And we can see that India is now separated in on its way northwards. Australia and Antarctica are still connected. And we're just starting to open up our patch, the North Atlantic. It opens 55 million years. It's going to be 5 million years. And one strand tries different ways. It's not really sure. There's one split that goes up Baffin Bay, Greenland area. There's another one that thinks about going up the North Sea, creates the North Sea. It doesn't quite happen. But the main one then is going to rip through here, and we're going to separate Greenland and the UK, and part of that plume that's under there driving it is going to break through and create Iceland. So Iceland doesn't exist at this moment. And I just think that's extraordinary. I think that is amazing that it sounds this legendary, almost biblical epic event, and yet it is absolutely mainstream science. There's nothing very controversial about that if you're a geologist. The driving force for this, I said earlier that evidence was put forward in around about 1915, 1920, the evidence came together that there had been this continent, this supercontinent. But it was rejected, so even though the geology fitted, the physics didn't. the mechanism was unclear. Wegener, who was the German scientist that put forward this idea of the drifting continents, couldn't provide a viable mechanism, and the ones he did provide were just laughable. And really, as a result of that, of not being able to provide the physics behind it, it just kind of died a death, really, particularly in the UK and Europe and North America. And the irony was that there was a mechanism there, certainly in his lifetime. And that was this notion, this is how we presently understand this mobile Earth, is that we've got this outer rigid shell of the planet. We've got an interior that is a heat machine, losing heat, provides heat to this outer part as part of a convecting system. And then what that drives is the most amazing recycling machine, whereby we have new crust that comes out at what we call mid-ocean ridges here. So that's the new formation of crust. And then that cools and kind of moves on a kind of conveyor belt down and eventually goes back into the Earth along what we refer to as subduction zones. And that recycles not just rock, which is important enough, but also all the elements, gases, water, everything that keeps Earth active and an active planet is because of this huge recycling system that goes on. And this idea of convection as being the driving force was one that was recognized way back in the early 20th century. And it was really recognized by this guy, Arthur Holmes, who was at Durham originally and then went to be professor of geology through at Edinburgh. And Arthur Holmes is one of the truly greats of geology. His principles of physical geology has got just about every geologist I know through university, myself included. I don't know what edition I had, I can't remember now. But the interesting thing about Arthur Holmes was that he when everyone else was just dissing this idea of drifting continents, he kind of got it. And he, in his book, the very last diagram in his textbook was this diagram. And where he talks about the fact that there was these continents and oceans, and you can see underneath here this idea of stuff coming up, heat coming up, and very clearly a notion of continents being broken, and also very clearly this idea of descending back down. The main elements are there. And the caption to that diagram is just beautiful, because it says something like, if this continental drift idea has got any truth in it, then maybe this is some kind of mechanism. So he doesn't say he believes it. He just says, look, if you're going to believe that, then there might be a mechanism in place. Unfortunately, Wegener's evidence really didn't get put together with Holmes's convection currents until really the 1960s. So until the 1960s, this idea of a mobile Earth wasn't put forward. And now we call it plate tectonics, and it's part of the school curriculum. But if you were if you were working in 1960 in geology and you believed that the plates or the continents moved, you were laughed out of academia. You were very much in the minority. If you didn't believe they moved by 1970, you were laughed out. The transformation really happened in about 5 years, extraordinary. And now Arthur Holmes's convection currents are a fundamental kind of part of the way we see this. He made other huge developments as well, but that's the one I want to mention in this context. And the reason why he had this actually goes back even more. So when you go back further, almost everything in geology roots to one key person, certainly in the kind of Western thought of geology, and that is that guy. It's called James Hutton. And James Hutton, there was a big debate, really, about where rocks come from. Many of them, so there was an argument at the time that rocks were all laid in this kind of primordial ocean, laid down and kind of changed. But other people thought that some rocks were molten from a melt and actually crystallized. And this is a place in Glentilt in Perthshire where Hutton recognized that this is a pink granite, and this is a kind of country rock. It's a kind of hard, call it a metamorphic rock, but it's a hard country rock. And what you see is little bits of this rock injected into this rock. In other words, the pink rock must have been molten to be able to get in here and intrude and inject its way through. And this is one of a number of places where Hutton demonstrated that some rocks had to be molten, and that meant hot enough to melt. And he's got this quote about what he thought was the driving force, one of the counter effects to the destructive elements of erosion, what actually constructed the Earth. And for him, it was the internal fire, the power of heat, a force of irresistible expansion in the body of the Earth. So heat driving its internal engine was central to the way that Hutton saw the Earth in the latter part of the 18th century. And he stole that idea in the best possible way in terms of scientific, the way we should steal ideas, from James Watt. So James Watt is over this side, tinkering away on steam machines, making them more efficient. And this notion of just how powerful an agent of action steam was very impressive to James Hutton. So James Hutton really cottoned on to this idea that heat could be a process of change. To appreciate the next bit, you have to kind of realize that for us, James Hutton is this slightly godlike figure in geology, as close as we'll get to one, of someone who was of enormous repute. You can see him there. Look at him. He's obviously a very important and very careful and measured person. And so the next bit I really loved finding out about, because he's obviously someone with a sense of humor. He writes to James Watt at one point, and he says this. He said, "A smith here has been consulting me about taking a patent for some improvement of a bed. I'm thinking of adding it to a machine which should be called the muscular motion, whereby all the several parts should be performed of erection, intrusion, reciprocation, and injection." And James Hutton's talking about a steam-powered sex machine here. There's no getting away from it. So clearly, steam was something that was in his thoughts kind of constantly. I want to talk about other things, because it's not just in that area that we've learned can reinterpret the Earth. So I want to go to the Northwest Highlands. And this is the area of the Northwest Highlands Geopark, Knockin Crag up in Assynt, one of the most kind of classic places of landscape and geology that we have in Scotland. And this was the site of one of the great mysteries, or one of the great controversies, really, of late 19th century geology, where there had been an idea that the way that the planet is that you just have the rocks get laid on top of each other. So the oldest ones are first, then the next ones, and then the next ones, the next ones. And that the geology of Scotland was actually very simple and was part of that stacked sequence of rocks. The trouble was the people who actually worked in this area that knew the local geology thought that wasn't right, thought actually that it was the opposite way around. The older rocks were on top, and that made no sense. And so it made particularly no sense to Archibald Geekie, who was the head of the Geological Survey, and he'd developed this theory, and people were kind of saying it was wrong. So he decided that what he would do is he would send in his best mappers, the mappers before Stewart that was doing it, the BGS. And they would go in, and he would get his best team, and they would map, and they would prove him right. And so he sent in, these were the two leaders of that, Ben Peach and John Horn. So they brought all the kind of teams from all over, and they said, right, for the next 10 years, you're going to work on the geology of this region. And what was the problem? Well, the problem was this cliff line. This is Professor Rob Butler at Aberdeen University, kind of illustrating it for us. But you can see the layering. So there's a whole set of layers. So in the original scheme, this would be the oldest rocks down here, and this would be the youngest. But the problem is that this rock up here is actually more primitive, because actually there's no fossils in that rock, but there are some fossils in this rock down here. So across large parts of this area, this is the rock. The upper one is the one that is what we call the basement. So it's upside down, or it's at least in the wrong place. And when the Heavenly Twins were called, Peach and Horn, arrived to kind of sort it out, the people who had been dissing this big scheme both of them took the geologists to this particular place, and they said, this is the problem we have with your boss's theory. And The key thing is, the key way in understanding, this was developed by a Galashiels school teacher called Charles Lapworth, was that little layer in here where Rob's hand is. There's a really thin layer, just a few centimetres thick. And Lapworth recognised that the rock in there was very distinctive from what was above and below. And he described it, that the rock looked as if it had been crushed, that it came in, the layers came in, and it looked as if it had been crushed, as if it was like a rolling steel mill, where the steel comes in and gets thinned out. And a crushing mill of irresistible power. And that rock actually got a name from this particular location. It was called a millenite, or as geologists refer to it today, a myelinite. And the point was the realization that that rock there was because what that had happened is the rock above had actually been pushed up and pushed sideways for tens of kilometers. So what had happened was you have the rock here in the basement, and then it gets pushed up and over and thrust on top of the other rock. And this process had been kind of guessed at a little bit in the Alps, but this was the first place where it got really described in detail. So we now have, for example, just in the background here, there's a line along this area here. Oops, let's go back to Rob. Let me just jump ahead. That line here is what they refer to now as a thrust fault, whereby a whole slice of rock hundreds of meters, kilometers thick, can get pushed up and over or on top of another one. It's an extraordinary idea. Because until then we thought mountains had to be just kind of shunted together and kind of just pushed up. But now we're saying we can actually create them by pushing on top and stacking them up. And people played around with this. This is Henry Cadell, who started with part of their group and started doing these little pressure box with muddy layers here and basically squeezing them together to produce topography. And here's me on the edge of Loch Horn, I think it is. No, it's not Loch Horn, but it's up near, just up near south of Knockin. Playing around with the same thing. And just to kind of show you, what happens is you put layers on here, and then you tighten that box, and you end up getting this. You end up getting the layers thrust on top of each other. So just by shortening the rock, you actually increase the height. And so we now, from this area, we understand a fundamental way of understanding mountains. I love this quote from Geeky, because he talks about, he was a beautiful writer. I don't know many heads of the Geological Survey that would write a chapter on poetry and geology, but he did. But he's got this quote, "Men will be taught that beneath and behind all the outward beauty of our lowlands, our uplands, and our highlands, there lies an inner history, which, when revealed, will give beauty a fuller significance and an added charm." What I think he's getting at there is you can look at that place, that happens to be looking onto the Coolins, but anywhere in the Highlands, you can look at that and think, that's beautiful, that's amazing, look at that. And we do that all the time. But actually, when you also understand the scientific significance and how it's formed, it almost takes on an even bigger order of magnitude of how amazing the process is. Because now, thanks to these two and their team, you can go to any mountain belt in the world, and this is the Himalayas here, and you will find thrust faults, and you'll find that same process building mountains, something that was discovered in the Northwest Highlands of Scotland. Second bit really is about time, and I don't think you could do a talk about geology in this way and not show this place. This is a place called Sicker Point in the North Berwickshire coast, and it's where people argue deep time was kind of discovered. I'm actually going to show last summer I went there with some students from Glasgow University just for a jolly for the day, and I made a little YouTube video, and I thought it'd be a nice contrast to all the fancy BBC types, is to show my little YouTube video, which is out there on YouTube. So this is the first time it's ever been seen in kind of a public talk. So let's see.
It was in the summer of 1788 that James Hutton first came here to make a discovery that would transform the way we think of our planet. He came by boat with 2 companions on a day when the fineness of the weather allowed him to hug the rocky shore. The generations of young geologists that have followed in his footsteps have taken a more direct route, clambering down the steep grassy slope to the wave-pummeled platform below. For some, it's a pilgrimage, because this is hallowed ground. What Hutton found here that day is celebrated as one of the most important geological discoveries in history. Two very different types of rock. One said, marine sandstones and slates from the Silurian age, 430 million years ago, project up as vertical ribs.
Geology in motion.
A ragged, eroded surface cuts across these layers. On top, a set of gently sloping beds of red sandstone. Old red sandstone. Remnants of a scorching desert 360 million years ago. Hutton realised that the vertical beds had been laid down horizontal on an ancient seabed that had been folded and rotated, lifted up and eroded, and that later red desert sandstones were deposited on top and then tilted. Hutton's genius was to realise that what this needed was immense amounts of time. One of his friends who was there that day reported that the mind seemed to grow giddy by looking so far into the abyss of time. And while we listened with earnestness and admiration to the philosopher who was now unfolding to us the order and series of these wonderful events, we became sensible how much further reason may sometimes go than imagination can follow.
The closure of the Iapetus Ocean formed the Caledonian sequence. And we then have a period of erosion, and then the old red sandstone is deposited. Now, the time gap between the two is about 65 million years. The time gap between this being deformed and eroded, etc., and that being deposited is 65 million years. There's a gap here in time.
And so it was here, on this pretty ordinary stretch of coast, that the concept of deep time was born.
So this place is important because of this notion. What Hutton got there more than anything else was that if you're going to take an ancient seabed and you're going to be able to turn it up vertically, and then you're going to erode through it, and then you're going to have a desert put on top of that, and then tilted, you need time. And he didn't know how much time, but he knew it was a long period of time. It was much longer than the kind of biblical timescales that were getting put around for how old the Earth was. So that was quite heretical and revolutionary and all the rest of it. And so this is his famous final line, really, that we've seen a succession of worlds in Scotland, and that from this we can include it as a system in nature, and he kind of makes it akin to the systems that are in the solar system. And then the last line, the very famous one that almost every geology student knows, that the result there for our present inquiry is that we find no vestige of a beginning, no prospect of an end. In other words, that we've just got this kind of recycling system that's going on and on and on and on ad infinitum. And so this idea of how old things are and when it will finish doesn't really come into it. But we do know about time, and we do know about certain aspects. And I like one of the most interesting stories, I think, about Scotland's early past is from this rock wall in Rhynie in Aberdeenshire. Because that rock wall is largely made up of bits of stone that were messing up the farmer's plough in the field. So they'd be ploughing the field and they would hit this really hard black rock, and they would go, they'd swear away, and they would pick it up and they would stick it by the side of the field to produce these walls. And here we've got someone holding one of these rocks, because they're very dull when you look at them the outside, but if you cut through them and polish them, they are extraordinary. And you get this, what you see here is a kind of a whitish kind of rock with these kind of lines coming through it. This whitish rock is a hot spring. It's a volcanic hot spring. This was an area where Aberdeenshire was a line of hot volcanic fumaroles and all the rest of it. And these are plants. These are little plants coming through. That's the stem of them. In fact, actually, if you cut into that, you can actually see all the cuticles. You can see all the structures, the cells of those. But it's not the first plants, first land plants in the history of the planet. But what you also find in there is invertebrates and other things. This is argued to be the first ecosystem that we see on the planet in a stone wall in Aberdeenshire. And that would be the kind of very, very simple plants that we would be getting. So this is the first start of really complicated environments of life preserved in a rock and kind of left to us by farmers on the side of the wall. So we through vegetation, I did a series called How to Grow a Planet a few years ago, and really kind of tracked back in time. And I just want to take you through some of this stuff as it relates to Scotland. So land plants come on land, basically, at about 420, 430 million years ago. I do appreciate that I just chuck around these words for, 400 million, 300 million. They are very easy currency for us. I'm not really sure I understand what a million years is any more than you do, so I apologize in advance that I'm just throwing them out. But anyway, plants arrive, and from plants we can get, based on looking at their stomata, the little cells, the holes in the leaves, we can get an idea, for example, about how oxygen levels have changed through time. So this is kind of a reconstruction of oxygen levels going back hundreds of millions of years based on looking at fossil plants. And that's one of the brilliant things about geology, is that we take from everything. We steal from every science. It's a derivative science. We take from biology, from botany, we take from physics, we take from chemistry, we take from anything we think will give us a chance at getting something. So one of the things that we see, just to go back to this, is that what we see is that as soon as plants come on, we see changes, because they actually change the amount of oxygen that we get. And what we see is that as we start getting more and more plants, and plants start to take off, huge forests start to very quickly go around, we see oxygen levels rise and rise and rise. And so 300 million years ago here, we have oxygen levels that are about maybe 35%. Now, oxygen levels today out there is about 21%. So it's a really dense, oxygen-rich environment. And as a result of that, the life out there is very different to what we have today. So this is the time when dragonflies are about 1.5 meters across, because there's a density to the atmosphere that means that they can fly, for example. This is the African giant millipede. Just there, one of the biggest millipedes that we've got on the planet. That is the track of the equivalent in the Carboniferous. See that double track coming through? It was the size of a tiger. It was the length of that. So that huge amount of oxygen that was in the atmosphere actually meant you could get giant organisms, because they kind of forced air into them. But that didn't last. But the other thing that you get, because then the oxygen levels went back down, and one of the reasons for that was such an oxygen-rich environment, there were lots of fires, because it's a combustible material. But those sediments, that rich vegetation that was dominant in the Carboniferous, leaves behind a really important legacy. So what we see, if you could just see this is where plants come on. And what we get, this is for CO2 this time. So obviously plants, just go back to science, so plants will be taking in carbon dioxide from the atmosphere and pumping out oxygen. That's kind of what they do. And so when plants come on, we see global carbon dioxide levels plummet and plummet and plummet until 300 million years ago. That warming effect that carbon dioxide has as a greenhouse gas disappears, and the planet goes into an ice house, a kind of glacial conditions as a result of that. So plants and their growth with forests bring on an ice age. But it's temporary. So that around here, this is the Carboniferous. It kind of goes back up again, because we end up getting these great areas of forest get burnt by the high oxygen levels. But the key thing that gets left behind is this. This is from Crail. And if you go into foreshore in Crail, you can see tree trunks sticking up from this carbon age. And really, the importance of this, apart from just being amazing, apart from the fact you can go to Crail and stand there being a 300 million year old tree, is that it leaves behind this. The great coal deposits of Scotland, the UK, and right across North Europe and Northern Europe and Western America. So our massive coal deposits that essentially sits really underneath the kind of economic riches of Scotland came from that very short-lived period of time of high oxygen levels and that really intense amount of vegetation. And the other thing that came from the Carboniferous is oil. And this is the bings of kind of Bathgate in the area of the Central Belt. An area that was, in the 1850s, the site of the first great oil rush in the world, spawned largely by this guy, James Paraffin Young, who was born in 1811 in Glasgow, chemist, went to Anderson. He was a joiner, I think, went to Anderson College, just started learning chemistry. And then by the time he was 26, he was a lecturer in chemistry at UCL in London, and really pioneered the ability to take, in this case, a local shale oil called a torbanite, and basically crack it and release the hydrocarbons. And so for a very short period of time, he got the first commercial patent for cracking oil, for oil fractionation. He then produced the world's first commercial oil works. And in 1865, his oil works at Bathgate was the biggest oil refinery in the world. Now, very quickly, the center of gravity moved to the US and to the Middle East. But for about a decade, Scotland was the center of the oil industry, and this was an oil kingdom. And those are from those Carboniferous rocks from that particular time. And the key thing, I guess, is that how much of Scotland's industrial wealth comes from this particular era. There is a downside, though, and here's the downside. So, middle of the 19th century, when Scotland Monument was built, if you looked at the carbon dioxide levels in the atmosphere, it was about 240 parts per million, or 290, parts per million. What we see is, so right back here, we've got about 290, so there we are, sitting in here somewhere. These are measurements in the ice cores of what the carbon dioxide levels are, starting at 1750. So if you like, in the time of Hutton and Watt down here, we see it rising gradually. But then what we see is this rise around here, so that I'll show you one in a second, the steady increase in CO2 levels. And that is because of the downside of these greenhouse gases, the burning of coal and oil, the fossil fuels, and putting CO2 back into the atmosphere. And so we've had about an increase of about 100 parts per million in the last 150 years. Now, it's at this point that people go, 100 parts per million. Listen to what you're saying. That's a tiny, tiny amount. Well, this is the record of the CO2 over the last almost a million years, and we've got this from the ice core records. So you can see, unfortunately, it just goes off the screen here at a pretty crucial point. But here's the level that we're talking about. And basically this here is the rhythm of the planet going, when it's very low CO2 levels, that's when we're in an ice age. And when it's high up here, that's in what we call an interglacial, like a warmer phase between the ice. And what you see is, for the last million years, we've just bounced in and out of ice ages pretty regularly. So you'll all hear this all the time, the climate's always changing, and it clearly is. The interesting thing is that starts, if you're in an ice age, it's about 180 parts per million. And if the planet's not in an ice age, if it's in a kind of greenhouse stage, it's 280 parts per million. So 100 parts per million is enough to send the planet in and out of ice ages. So the planet's climate is incredibly sensitive to these little nudges. And the point is, we've put 100 parts per million in, well, actually, since about 1900. This graph goes off the scale here. It goes up, the present parts per million is 400 parts per million. And that is something that really has been produced by us, by humans. Just someone who deserves a whole talk on their own, but one of the people who actually worked out that rhythms of the Ice Age, in and out of the cold phases, was this guy, James Croll. James Croll was one of these classic kind of self-taught people. Went through a whole series of slightly dead-end jobs in his career and ended up as a janitor at Underpin College, which is now Strathclyde University. Him and his brother. And James Croll kind of made his brother do all the work while he went to the library and he read all of the great kind of texts. And basically he taught himself astronomy and physics and kind of science. And then he started writing papers and sending them to the Royal Society. And the Royal Society were very impressed by them and would send back to Professor Croll. And of course, he was a janitor, so he would intercept the post. And so it took a while before people realized that the janitor was the guy that was writing all these amazing papers, and the Scottish Geological Survey signed them up. But I think what's interesting here, I mean, there's a lot of stuff that Croll got wrong. He basically understood that one of the fundamental points was our relationship with the sun. How the Earth orbited, how it tilted in relation to the sun, and that was all entirely predictable. So he said, well, if its orbit and its changes are predictable, then we should be able to predict how much radiation, how much solar radiation the planet receives in a way. So he did that, and he calculated out, and he worked back. But the interesting thing here is, there he is, there, and he actually projects forward, and he predicts what we should have. And that's really interesting, because I mean, a lot of that's been refined now, but one of the big arguments is, and it's very, very current, like, papers coming out as we speak, is that there's a feeling that we should have gone back into another ice age. That the cold phases of we look at these solar insolation kind of cycles means we should be on a cooling trend, and yet we're obviously not going back into another ice age. And so this final little section is about that, because the reason that we've not gone into an ice age is essentially because of this human element that we've created really in the last few centuries. And it could be argued started in Scotland, either with James Watt and the steam engine and that industrialization that kicks in, that allows the coal industry and mining and all this great industrialization that gave us our Victorian wealth. And this notion is that we've moved from a planet that kind of behaves itself, works out its own kind of dynamics, to one where we, humans, are actually a driving force. And that's extraordinary, the idea that we humans can be something that can shape the way the planet's behaving. But actually, if you get a sense of that industrial age, then, and this is from Thomas Carlyle, you get a real idea of this. This is him writing The Mechanical Age in 1829. We remove mountains, make seas our smooth highway. Nothing can resist us. We war with rude nature, and by our resistless engines come off always victorious and loaded with spoils. That is what made our country. That ability to go down into the earth and exploit its mineral riches and build our country up into great wealth, and to go around the world and to do that in lots of places, and other countries have then followed suit. But what it's meant is that we've shifted into a new gear. We've shifted into what people are referring to as the human age, the Anthropocene. We've moved out of one that was dominated by climate and one that's dominated by humans. When that started is a great debate amongst geoscientists. Some people say it's the James Watt thing. Other people say it's much later. This is a whole series of graphs about socioeconomic things. So basically things happening on the planet. This is world population, GDP, foreign investment. And this one here is how the Earth works. Now, you can't see the dates on here, but in all of these graphs, 1750, so James Watt, James Hutton sits at the left-hand side, and today's at the right. And what you see is, you might just say a line, probably can't. There's a line coming down here about there, and that's 1950. So certainly in the post-war era, we go into overdrive as a species. Almost every action we're doing is heightened. So we've got urbanization going on, there's a post-war economic boom, everything is just going crazy. And so certainly in the second part of the 20th century and now, humans are a major driving force. So one of the ways, for example, is fossil fuels. So this is the North Sea. and oil rig in the North Sea. And what we see, for example, that started really 64, 65 for gas, 69, 70 for oil. And what we see is a kind of rising increase in the amount of oil hydrocarbons getting found in the North Sea. And then it kind of peaking and then kind of descending back down again. And so fossil fuels are a fundamental part, again, of our kind of rich wealth, but there's a downside in this as well. Because we're now, many of our resources are starting to decline, and we're all too aware of that in the news. And other things too, is that slight kind of desperation for energy really is forcing us to look at new ways to try to eke out this continuing kind of supply of hydrocarbons, for example, from things like shale gas. But the key thing then is this tension in the air, a discernible tension between getting the stuff out of the ground that we need to supply the modern world to run and the detrimental things that spawn from that. And particularly this one here is something like climate change, which is now a spectre that sits amongst it all. And there's other things like we're looking at. I mean, this is something very close to home, the idea that maybe one way that we can kind of keep going and have our cake and eat it is by something like carbon capture and storage. So maybe we can take carbon from things like this as a power station at Peterhead, grab the carbon dioxide that would be going up into the atmosphere, and then kind of reroute it, kind of reverse engineer our oil fields and put the CO2 down into the oil fields from which it came in the original kind of place. Now that's kind of stymied at the moment, that's kind of in a hiatus, but it's one of the arguments that says that this is a technology that's there, and this is a technology that's been developed obviously in Scotland, and therefore could be some big new investment. But the point really, the broader point, is that we're at this stage where, this is an environmental thinker called Thomas Barry, says, we're at the present time participating in unparalleled change in the human Earth situation. The planet that ruled itself directly over these past millennia is now determining its future largely through human decision. Our decisions about how we want to live our life are actually having really big effects on the planet for the first time ever. And that, I think, is an interesting paradox for geologists themselves, because geologists are a little bit in two worlds. The top one is the majestic, that's me, majestic on an ice sheet, thinking that the geologist is the person who understands how the planet changes, its rhythms, its feedbacks, its intricacies. We know where its maybe tipping points are, etc. So if you want to save the planet, trust the geologist. We can look after the planet. We're a steward. But the flip side of being a geologist is we go out and find stuff. We get stuff out the ground, and you need it, because you need your phones, and I need my phones, and cars, and all the rest of it. So we find commodities, and we're really good at finding it. So this is obviously the oil and gas fields of Azerbaijan. But those two, the idea of us exploiting the planet and also being a steward, are a tricky balancing act for us to do. But that's the geologist world. And this is my backyard, or my home backyard in Feast Kilbride, so Whiteley is just up the road. And the interesting thing is, there was an alternative history, because in the 1880s, this guy, James Blythe, invented the first commercial wind turbine. And he lived in America, near up in Aberdeen, and he invented this thing, and it was in his backyard, and he used it. He was a lecturer at Andersonian College. He invented it, and he had a shed where he stored the batteries, and so this kind of thing ran, but it made extra electricity, and he offered the extra electricity to the citizens, the good citizens of Marykirk, and said, do you want me to light the main street for you with this extra electricity? And they said no, because electricity is the work of the devil. And so instead what he did was he set up a turbine at a local mental institution, and it ran for 30 years producing electricity, the kind of first one. And the reason was that he thought that wind and water was a much better long-term energy source than fossil fuels, even at that time. He called them the wicked middlemen. That this was some kind of ineffective kind of process ultimately doing it. But of course, we've never heard of James Blythe. This thing goes into nowhere. And instead we go down to fossil fuels. And now, belatedly, we kind of come back to these things. So there was a whole set of parallel worlds. But I want to finish on Hutton. Everything roots back to Hutton. If you open the first page of his Theory of the Earth in 1788, he says this: "This globe of the Earth is a habitable world, and on its fitness for this purpose, our sense of wisdom in its formation must depend." Hutton realized his whole theory of the Earth was about the physiology of the planet. He did medicine at Edinburgh University. He wanted to be a doctor. He was interested in the circulatory patterns. He saw the planet's health and well-being as being a fundamental thing about being a geologist. And I think that as we look to the future and think about what kind of planet do we want, it seems to me that geoscientists, people that study the Earth, have a fundamental role to play, because they can actually be this bridge between these two very different worlds. How to understand how healthy and the well-being the planet's system is, the Earth economy, if you like. And then the other side, which is delivering the economy that people need for development and progress and all the rest of it. For Hutton, there was no problem with this. That's what geology was about. That's the reason we go back and try and understand the planet, is in order to have that good sense, that wisdom to be able to make our decisions about the future. And I think that we need more than ever. Thank you very much. We don't really understand how it works. So we know that it operates and they get these cells, but the relationship between these convection in the interior and the intricacies of the plate movement is quite hard to see. If you go to the Atlantic, what you see is you see that pattern in the Atlantic. You can see it very clearly. It kind of, the ridge at the center comes down and jumps across and is very changeable. That doesn't fit very well for a nice simple blob of stuff coming up, because why do you get all the detail? So what it seems to be, and this isn't very satisfactory, but it seems to be that convection is the driving force, but the way that the plates actually move isn't a direct thing. So that particularly very simple one had the thing coming up, going aside, it was very simple, the plates move. It doesn't really work that way. And the reason we know that is because, as you say, you can go to places with quite small plates and little blocks and things like that are all moving, but aren't really related to any big convection cell. So what it seems to be is that convection sets up the whole big picture, and then there's lots of little fragments that all must take care of themselves. They have their own kind of life cycle. So you're absolutely right. What you get in Indonesia is you get the Indian Ocean, Indian-Australian plate getting pushed underneath the Philippines plate and producing earthquakes and volcanoes and all the rest of it. And it's not really clear that that relationship is driven by some kind of convection coming there. It's a part of a bigger system. Partly, and I think the other thing about plates is that the real driving force that really continues is when you get we call it subductive, when a plate goes down underneath, that weight of that really cold slab of rock pulls. And so when you get it, it actually starts to create its own momentum as well. And that's one of the big driving forces. So as I say, this simple notion that we get, and it comes from school and comes through, by the time you get through halfway through your undergraduate, you have to start really questioning some of those basic bits. I'm going to take the easy one first. The easy one, amazingly, is how did Pangaea come together? So one of the arguments is that whole process of continents coming together is part of a cycle. So you basically have, it doesn't really matter where you start. Let's start with them scattered. You've got them scattered and you've got a subduction system in here. So one plate's going down. As it goes down, that basically is destroying the ocean. So the two continents come together and eventually kind of combine. The reason then, so that process is happening in lots of places. So you'll get it where the various parts of continents start to bang into each other. And then what happens is it sits there for a while. Now what you're trying to get, you've got a system of trying to lose heat. So at some point, you can lose heat in the ocean, it's dead easy. But when you've got a big thick continent sitting on there, that's difficult. So that heat then eventually just tries to get out, punctures it and splits. So that the argument is that we call it a supercontinent cycle, probably happens every 500 million years. In other words, Pangaea wasn't the only one. You can go back in time 1 million, a billion and a billion and a half and find other supercontinents. So we think it happens again and again. It's part of that gross fertility cycling. In terms of, and I think it's true, I think we have created, it's like your second part of the question, we have created a new Pangaea, that actually we've got these scattered continents. But you can go onto your computer and you can Skype across the world, or you can go on a video game and you can be playing a video game with someone in Australia, someone in America. The digital age has really connected the planet in a way that we feel that we're all connected. Quite what it means for, in terms of human-driven, I think that many of the, I guess in a very obvious way, many of the materials that we need for this new digital age are coming from very rare critical metals that we've never had to necessarily use before. And that is sending geologists to new places to get it. So for our phones and for our kind of screens and our computers and things like that, are minerals and metals that might be found in one little place or a few little places. So we're getting rid of some things. We're not going to necessarily, coal, for example, hopefully is kind of, in a way, is a global kind of source, but there's other things that's coming in. So you'll always be needing some geologist somewhere to dig stuff out, I suspect. And because of that, you then have this ethical issue, this responsibility issue about how we do that in the best possible way. I think that might end up being one of the trickiest things about being a geologist in the 21st century.
I'm going to ask the corollary to that thing. So as we're playing around with all this digital kit in 250 million years' time, where's Irvine going to be?
Irvine's probably going to be under the North Pole.
Yes.
The rest of Scotland will be somewhere else in the tropics, but Irvine will be up in the. No, Scotland has had the most incredible journey. So if you go back 500 million years, Stuart will tell me if I'm wrong here, but Scotland nestles down in the lower latitudes, or the higher latitudes of the southern hemisphere, and basically drifts northward steadily through the lower latitudes of the southern hemisphere, across the equator, through the desert latitudes of the northern hemisphere to where it is now. So the expectation, and we don't really know how that next one will play, but the expectation is that drift will continue. So, forget global warming. If you've got 200 million years, if you want to go for your holiday, you're going to be under a kilometre of ice probably. So just bear that in mind. So the question is about fracking. I think there's two elements. Oh, everyone, sharp intake of breath there with people. I think there's a multitude of aspects about fracking, but I think I would separate them to do two different things. One would be the scientific and technical aspect, and the question about whether you can do it safely, and I think the answer to that is yes. And the reason I say that is because it is a technical industrial process, and all of the aspects about we do before we do routinely. I think the problem with it is almost in the same sentence. It's an industrial process, and industrial processes invariably go wrong because of human connections and all the rest of it. So the actual technical bit's fine. I think that for most geologists, that the bigger question isn't can it be done right, and that tends to be the question. That first bit is a bit that vexes most people. But actually, should we do it? And the bigger context about as we move from this high carbon fossil fuel past, we're looking to a low carbon fossil fuel future. And I think what's hard to see is how we could start an industry that is big enough to actually impact on our energy security and at the same time finish in 20 or 30 years, because we need to be getting out of fossil fuels in 20 or 30 years. But there is an issue here, and that is, as a society, we're completely addicted to gas. We use gas for, generally about 40% of our electricity. We use it sometimes for 80% of our central heating. We use it for industrial processes, producing plastic, fertilizers, a whole set of things. Our domestic gas out in the North Sea, which we've been perfectly happy to exploit, or we've been ignorant of it in the sense we've not seen it, is declining. We're perfectly happy to then import gas from places in the Middle East like Qatar, whose environmental and human rights records are very questionable. We don't question that, we take it in here. So I do find it odd that we get very fixated about this issue, about whether we should take gas from domestic gas from our backyard, but are quite happy to accept it from the other side of the world, no questions asked. And I do think there's issues there. I think you could tell I'm in the middle with this. I think we need a grown-up conversation about where we're going to get energy. I think most geologists would be perfectly happy not to go down the fracking route. I think what geologists want to know is, what do you want us to do for energy? Where are we going to get our energy? And once that gets sorted out, the geologists will do their bit about going to do it. But I think at the moment, what tends to happen is that we spend most of the time saying about what we don't like. You know, I don't want fracking. I don't like nuclear. I don't really like these wind turbines. I don't really like solar because it fails, it takes over things. And we end up in an impossible situation, and it will get imposed on us. So my view is that I suspect that as an industry, fracking will struggle to take off. But I do understand the impetus for it, because we have this huge diet for consuming gas, and that has to come from someplace. And if we're not going to do it here, it's going to happen in some part of the world. And I actually would trust the environmental regulations and the science and the technical stuff here far more than I would in the other side of the world. And so I'm kind of ambivalent in the middle. Yeah, geothermal, actually, you say that at a time of real resurgence in geothermal. There's a whole set of projects. In fact, there's a whole set of projects just gone in this week to the Scottish Government trying to push forward a few geothermal projects. At least one or two will come off. Down in Cornwall, they've just released there used to be some geothermal there, they've released a new call. It's probably going to be good. I think for community heating systems, it's got a very good chance. And we were chatting earlier, the coal mines, the mine waters around this area, and that's a tremendous problem of what you do with these flooded mines, but those are warm waters, so we can use that. There's also the deeper geothermal that can produce power. So I think that'll happen. I think there's the issues is that it's a scaling thing, really. We demand a huge amount of energy, and geothermal is going to be okay for certain places, but I definitely think we should be looking at it for community heating systems as a very efficient way, ground heat. Where's my favourite site? That's an easy one, but it's very personal rather. It's Rassay in our Hebrides. So if you go up to Skye, you'll get to a little place called Sconson. There's someone nodding there. It's go across, and I love it because it's a small island, but the geology is very varied, and it's where I learned to be a geologist, and so that'll always be my best one. But I tell you this, it's really funny. All these programs going around the world, these are the most amazing places. And then I filmed Men of Rock for 4 months, along with another one called Making Scotland's Landscape. And there were several times in filming that where I would go around a corner and I would just go, that is the most amazing place I've ever seen. And then I'd remind myself I was in Scotland. So I do think that one of the things that's amazing, that's great about going around and seeing how amazing the planet is and spectacular the planet is remembering how spectacular and amazing it actually is here. And you have to kind of go away to see that to some extent.
I'll let you off.
Thank you very much.